Well, let's go. So before we did chapter 42, which is the main subject of today, I'm going to work one example, and this is what's called electron tunneling. There is a device that's made in the electronics industry called a tunneling diode that uses this principle. You can look it up on Wikipedia if you want to learn more about it. But we haven't really gotten to diodes yet, so let me do this example. So basically, here's what we're looking at. Supposing I have an electron gun, and electron gun is a heated filament. Right? I heat up a filament, and I apply an electric field across here, and the electrons are accelerated across the electric field. Then, if I put, for every volt I put across here, the kinetic energy coming out will be equal to that number in electron volts. So the kinetic energy coming out here is 5 electron volts, right? So we do a case where I just put a very small voltage on, and this is how we create electron beams. You know, it's a heated filament and an accelerating plate and a hole in the middle for them to get through, and out comes the electron. Any question on that? Yeah. All right, now, what I want to do is I want to put in a retarding potential. Notice that I have set the voltages here so that the electric field between these plates is equal to 0. Notice that both plates to the right and left of here are positively charged, so I can set them so that their electric field is equal to 0. Now, at this point, the electrons drift. Now what I do is I put them through an electric field where the force is the retarding force F. And this is equal to minus the charge on the electron times, of course, the electric field, E. Okay? And this electric field can be in volts per centimeter. So, you know, for example, this will be E as in volts per meter or volts per centimeter. For use units right, it should be volts per meter, but this expression. Now, what I want to impress upon you is that if I apply a retarding voltage of 7 volts, which applies a deaccelerating force on the electrons, then the amount of kinetic energy that it loses is 7 eV. So if it only had 5 eV to start with, and I subtract 7 eV, then basically I would get a -2 electron volts, which means that the electron does not make it across. It turns around and it comes back out. In other words, the electron does not have enough energy to make it through the barrier. Right? I've accelerated with fewer volts than the height of the potential that I'm retarding it with. Right? Therefore, classically speaking, the electron can go into here, and it makes it almost all the way across, and it goes back out. You can see that? Right? The electric force on the electron is retarding it, and the voltage is high enough, it exceeds that the voltage that it had acquired coming out of the source. So, we would say classically that the probability of transmission T is equal to 0. Right? That the electron cannot make it through the barrier at all. Okay? Now, we know that as we derived last time, that this is exactly the case, and by the way, this is actually what I wanted to do. This was an energy diagram, so this would be the energy, and this would be the potential energy of the barrier, and the electron is coming in to the barrier at 5 electron volts, and the height of the potential barrier is 7 electron volts, right? So it doesn't have enough energy to make it through the barrier, but we know that from our formula we derived last time that there's a probability that I will make it through, and there was a term that looked like 1 plus P1 over P2, quantity squared, is 1 plus P2 over P1. I will redefine these terms here in a minute. And this is times e to the minus 2g times A. A is the width of the barrier. So in physical space, the barrier width here across here is what I call A. Okay? And g is given by the expression the square root of 2 times the mass of the electron times the height of the barrier, which in this case we'll call it u0 minus e. And in this case, u0 is equal to 7. U0 is equal to 7 electron volts, and E is equal to 5 electron volts. And I want to calculate the probability that it makes it through. And in fact, as we will show, the probability is not 0, but in fact, some of the electrons will make it through, and we can measure what fraction that is. Now, by the way, in my notation here, I probably can simplify things a little bit. This should be P2. Let's try this again. P2, and this would be. Let me check my notes, make sure I'm doing this so I don't miss out any. E to the minus, let's do it. E to the minus P2 times A divided by H bar. And this is the expression. Now P1 is the incident momentum. So P1 squared is equal to 2m times E1 squared. So this is the kinetic energy, E1. That's incident on the barrier. And P2 is equal to, or P2 squared is equal to 2m times U0 minus E1. And therefore, I can calculate the ratio of P1 over P2 squared, or I can calculate P2 squared over P1 squared, which is the inverse, right? So I'll do that real quick. So P1 over P2 quantity squared is going to be equal to, oh, by the way, this should not be squared up here. My mistake. P squared is equal to 2me. P1 squared, so this is equal to 2m times E1 divided by 2m times U0 minus E1. And therefore the masses cancel out. E1 is 5, U0 is 7. So this becomes 5 divided by 7 minus 5, which is equal to 5, which is equal to 2.5. So this is equal to 2.5. And the inverse of that, P2 over P1 quantity squared is equal to 1 over 2.5, which is 0.4. Right? Is that right? 1 over 2.5 is 0.4. Okay. So that means that we now have this coefficient to calculate out here, and this then becomes 16 divided by P1 over P2 squared is let's see, 1 plus this quantity squared is 3.5. And 1 plus P2 over P1 squared is 1.4. So I've got the first terms figured out. And now what I need to do is to calculate calculate P2 over H bar squared. So P2. So I now need to calculate this exponent. So I get P2 over H bar is equal to the square root. And now I'll put numbers in here. This will be 2 times the mass. The mass is 0.511 MeV. And U0 minus E is 2 electron volts, so I'll put 2 eV in here. and I'm going to divide by h bar, which is 200 EV nanometers. Okay. So I can evaluate this, and the number, and notice I have MEV times EV times EV, which is EV squared. If I take the square root, I get EV. EV divided by EV nanometers is inverse nanometers, and this number gives me 7.25 inverse nanometers. Okay? All right, so I'm almost all the way home. All I now have to do is to calculate what is e to the minus 2 P2 times the width of the barrier A. For this particular problem, I'm going to choose the width of the barrier to be, this width of barrier A to be equal to 0.3 nanometers. Okay. Roughly 0.3 nanometers. So now what I can do is put in the numbers here, and so this becomes e to the minus 2 P2 over, oops, I forgot the h bar, P2 over divided by h bar. P2 over h bar is 7.25, and the width of the barrier is 0.3. So putting in the numbers up here, I get e to the minus 2 times 7.25 times the width of the barrier, 0.3. And if I evaluate this, I get 0.004. And that's my answer. Okay? In other words, for whatever current I have here, let's suppose that I have 1 amp of electron current coming into the barrier, then there will be 4 milliamps that get through. And the rest of them will get turned around in the classical sense because they don't have enough energy to make it across. Okay? So the transmission is 0. So this means that if I have 1 amp incident, then this implies that I get 4 milliamps transmitted. 4 milliamps transmitted. Okay. So it's a way that I can accurately control very small currents. Notice that it's very easy to adjust this voltage. If I want less current getting through, supposing I only want a peak, instead of a milliamp, I only want a picoamp getting through, right? I want to reduce this by another factor of 10 to the 6th. Well, all I have to do is to make the exponent here a larger number. That means that I have to increase the barrier height. So if, let's say, for example, I change 7 EV to 700 EV, or I'm sorry, 7 volts retarding potential to 700 volts. Now this term in here becomes 700 minus 5, which is 695. And I'm not going to do the math for you, but you can see that I can very accurately control how much current gets through by controlling the height of the barrier. Okay? And there's a practical device that uses this. It's called the tunneling diode, and it's used in devices where you want to regulate very, very small amounts of current. And in fact, I can regulate down to femtoamps or down to picoamps or any other very, very small quantity of current by only allowing a fixed transmission through of the current. Okay? Any questions on that? Yes.
Where did you get the value for A again?
I made it up.
Oh.
I said, okay, let me suppose that I have a barrier gap that's 0.3 nanometers. Right? Now, I could have made it larger, by the way. I could have made it, that's another way, of course. I could just increase A, right? If I want to change the transmission of the barrier, if I increase that by a factor of 10, I could increase the barrier width by a factor of 10. And now this transmission factor would go down by a factor of e to the 10. So it's just a way to illustrate a tunneling through a barrier. Any questions? Okay. good? Yeah? Okay, good. All right. All right, so what we wanted, now we're going to start chapter 42, and we're going to go back to the Schroeder equation, and we are going to basically solve the problem of an electron in orbit of a charged nucleus. Charged nucleus. All right. And the first thing we're going to look at in this particular model is, let us suppose that normally the only element with one electron in nature is hydrogen. So if I took, for example, considered hydrogen, then for that simple case, then I have one proton and one electron, right? And because the mass of the proton is thousands of times higher than the mass of the electron, it's the electron that goes in the orbit around the proton, right? Okay, so we'll focus on this one for right now, the hydrogen, and we'll return to an experimental test that was done regarding the light coming out of a hydrogen lamp. So the idea of a discharge lamp, which is discussed in your book, is that I have a gas that's filled with low pressure hydrogen. Now we can use other materials as well, other gases, but for our purposes, we want to focus in on hydrogen. Because if I were to draw a simple orbital picture of hydrogen, then what I would have is the electron, of course, circling the nucleus, and it would be off at some radius from the center. And what we want to picture going on here now is that within this hydrogen, or around this hydrogen, there's our high voltage electrodes that are inserted in through the tube, through fused ports, and the high voltage here. And what happens now is that the electrons will be emitted from one of the terminals called the cathode. I'm sorry. Yeah, it's called the cathode. And as the electrons go through here, they accelerate to the positive side. So this will be the positive terminal, and this is the negative terminal. This is the negative. This is the negative terminal. And electrons that are liberated from here will be accelerated, and as they go across through the gas, they are going to interact with these hydrogen atoms. And in particular, the electrons are going to, as they cross by here, are going to interact, and they can do some changes to the hydrogen as a result of this. Namely, they can impart some of their energy. So these are an external electron, right? This electron is coming from the cathode of the discharge tube. And if this electron has enough kinetic energy, then it can excite this electron. So the idea that we now look at is that, let's look at the empirical results. The first thing to look at is what are the results of the measurements of the wavelengths of light. With hydrogen, there are 4 visible wavelengths that are observed. There's a wavelength at 656 nanometers. There's a wavelength at 486 nanometers. There's one at 432 nanometers. And there's one at about 410 nanometers, right? So these are 4, they go from the blue to the red. These are 4 wavelengths that are observed. And at the time that this was first discovered, we talked about this earlier, I believe, that a fellow named Rydberg came up with an empirical formula that basically said how to predict what these wavelengths how they are related to one another. So his idea was that 1 over lambda, and we'll call it lambda n, is equal to a constant r times 1 over 2 squared minus 1 over n squared, where n is equal to 3, 4, 5, and 6. And he discovered the value of r was equal to 1.09 times 10 to the 7 inverse nanometers, or inverse meters, I'm sorry. 10 to the 7 meters. And he came up with an empirical relationship of what the hydrogen wavelengths look like as a result of this electrons zooming across and producing wavelengths lambda. Well, in my notation right there, I could have lambda 3, I could have lambda 4, I could have lambda 5, and I could have lambda 6. There's only 4 wavelengths. Right? I'm just not starting with lambda. I'm not starting with lambda 1 because in my formula, n has to start with n equals 3. So I call my first wavelength lambda 3, I call my second wavelength lambda 4, my third lambda 5, and my fourth wavelength lambda 6. So, in this notation, this would be, the order they go in, let me think of this. Can't do that this fast on the top of my head, but basically I want to, let's see. If I have n equals 6, 1 over lambda is the longest, that means that lambda is the shortest. So this would be lambda 6, this one would be lambda 5, this would be lambda 4, and this one would be lambda 3. Okay? So these are the 4 wavelengths that I get from this, and this was called the Rydberg formula. Formula. Okay? It's the Rydberg formula. And basically it was an observation that there are 4 visible wavelengths that are observed in a hydrogen discharge tube. Okay? We've got 3 of them in the basement. I meant to bring one today, but hopefully maybe I'll bring it next week. But basically they look just like this, and when you plug them in, you see kind of a reddish light output that corresponds to the red being one of the more dominant wavelength, but you can kind of see, a mixture of perhaps other colors in it as well. By doing a spectrometer analysis, that is to say that we go through a diffraction grating, so if I put these through a diffraction grating, then at different angles, I can see different wavelengths. Right? And this goes back to chapter 35. Where we can actually use the diffraction grating like a prism, and wavelengths of the different wavelengths will get diffracted to different angles. Okay? And so we can measure these wavelengths using the formula that d sine theta is equal to m times lambda. Right? We solved this for lambda, so we measured theta. All right, so this was the empirical data that had been derived and studied by Rydberg as early as 1885. This data goes back to 1885. There was still no explanation for what was the physics, how do these wavelengths get produced. This is simply a formula that can show you how to organize the numbers, how to use a formula to calculate wavelength, but there's no understanding of what this formula means or what physics it corresponds to. So Niels Bohr was the first one to come up with the what we call the Bohr theory of the atom, and he was trying to tackle this problem very, 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 very precisely. And his idea was that, let's suppose that the electrons in an atom or their orbits are quantized. And that is to say that their energy is quantized, their angular momentum is quantized, the radius of their orbit is quantized. There are discrete values of orbital conditions of the electron in hydrogen. Right? And there's one which we call the ground state, which is the one here. But there are other orbitals that are possible at higher radii, and therefore correspond to higher energies as well. So this idea was that when an electron from the discharge tube goes zipping across here, it knocks one of the electrons up to a higher orbital. And this can decay back down to this way and then back down this way. Or it can go to a higher orbital, which it might go, let's say, up to here, and then it decays down to here, and then it decays down to here. And every time it makes a decay, where you see these dots, or change across here, coming down, it emits a photon. So there's a photon emitted here, there's a photon emitted in this case, there's a photon emitted here. Every time actually, it's gotten to be a very ugly picture right now, but the idea is that when the electron gets bumped up to a higher energy level, it can fall, it's going to fall back down to what we call the ground state. So the lowest energy level is what we call the ground state. And that's as far down as the electron could go because, according to Bohr, the energy of the electron in the atom is quantized. And so this was his model, that there are different orbitals available, that when the electron from the discharge tube excites the atom, the electrons go to a higher orbital and then they decay back down. And as they decay down, they give off photons that correspond to the difference in energy between a higher energy and a lower energy. Right? Similar to the way that Bohr was thinking about the black body radiation, with the oscillators could lose energy in discrete steps of h times the frequency of the oscillator. And this was equal to the energy change of the oscillator. And this became also of oscillator, which became, when it went down in energy, or gave up a certain amount of energy, HF, then this became the energy of the photon. So the oscillator could lose energy in units of Planck's constant h times the frequency, and when it did that, it gave off a photon. That was similar to what we talked about in the theory of black body radiation. So, Bohr's idea was that, notice he thought, thinking about this as an analogy, let's suppose I multiply this equation through by hc, h times c. If I multiply it through by hc, I get hc divided by lambda n is equal to r times 1 over 2 squared, r times hc, r times hc times 1 over 2 squared minus 1 over n squared, right? That is our formula. So his idea was that if this is the energy of the excited state, so he said this looks very much like the difference of two energies, the ground state, but that the energy, which I'll call E2 minus the energy En, is equal to the energy of the photon. Because remember, hc over lambda is the energy of the photon. Okay? So his concept is when the electrons get excited to a higher orbital and they start decaying down, then they will give off a photon that's equal to the energy that they lost. Everybody clear on that? Right? the picture of the orbital, the proton's in the middle. I've got one here, I've got one here, I've got one here, right? If I excite the electron up to, let us say, n equals to the fourth level with the discharge from the tube, or the discharge of the electron current from the tube, then this one will go up to, this will get jumped up to here, and now it can decay back. And there's multiple paths. It can go from here to here, or it can go from here to here to here to here. It can go from here to here to here. There's multiple steps in which ways it can come back down and to the ground state. So this is of course, what we call the ground state. Okay. This one, by the way, because we're talking about energy levels and orbitals, and we've already looked at this a little bit from the point of view of particle in a box, the ground state energy would be one where there's a quantum number n equals 1. This will be an energy level where the quantum number is n equals 2, and this will be one where the quantum number is n equals 3. Now, so far we haven't defined where those numbers come from, but it's a way of labeling the different energy states, right? Because we already suspect that they're going to be quantized by Bohr's condition, and we know that we only get 4 wavelengths out of this visible light from the hydrogen, and we have to be able to account for that. And his idea is that the photon wavelength that's emitted is caused by the excitation of electrons to a higher in state or excited state of the atom, decaying back down to the second state. And the second state is because I have 2 here that fits the form of the Rydberg formula. Now, using this formula, we can see that in this analogy then is that, or by this equation, that E sub n is going to have an energy that is equal to R times hc divided by n squared. Right? So if I write this as in this way, then, by the way, this should be En, I wrote this backwards. This should be En decaying down to E2, and there should be a minus sign here. So this will be equal to minus RC over N squared. Okay? So the decay is from a higher N state than N equals 2. Now you can say, well, why doesn't it go down to N equals 1? I can excite it from the ground state. Yes, it will come down here, and there are transitions, but they're not in the visible. It turns out that if the transitions that go down to N equals 1 are in the ultraviolet, and you can't see those without an instrument that detects ultraviolet light. Okay? So we are concerned with N equals 2 because this was the visible part of the spectrum, and these were called the Balmer. This is called the Balmer series because Balmer was the first one to discover or name these this phenomenon. Well, Balmer or Rydberg, I'm not sure which was the. I think Balmer actually came first and measured the wavelengths, and I think Rydberg is the one that came up with the formula. Okay, so now we have a theoretical understanding of what goes on. The way in which we get these wavelengths, these wavelengths that are observed, is from energy transitions. And now the problem is not over because how do I calculate and what's the theory to justify this equation? I mean, why is this equation true other than I think it's a good idea and it should work? Is there any underlying physics that will explain why this equation for energy is correct? Okay? So that's what he had to do. And if he can do that from fundamental physics, then he's made progress to understand how light is emitted from hydrogen. Okay? So that's the path that we're taking. Okay, I don't like this one. So the idea now is that we have to go back to basics and draw a picture of the electron and label its features or components. So the first thing we want to do is we will start with a charge of a nuclear charge. And this nuclear charge will be, if it was just an electron, then it would have a charge equal to, well, it would be equal to minus E, right? Minus E would be, or we would call this the absolute value of E, right? This is 1.6 times 10 to the minus 19 coulombs, right? If this was one proton. If, on the other hand, I want to talk about a nucleus with 5 protons or 10 protons, then instead of writing this as minus E, I'm just going to call this charge Z times the charge of the electron. And since the charge of the electron is equal to minus the charge of the proton, which is 1.6 times 10 to the minus 19 coulombs, then if there are Z protons in the nucleus, there is Z times E positive charge associated with that. Okay? And by the way, you can also see that on the periodic table if you want to know how many protons there are in any given element. As you probably know, this hydrogen has 1 proton, helium has 2, lithium has 3, beryllium has 4. As you go across, reading from left to right, the number of protons in the nucleus increases. So, for example, if I want to talk about copper, copper has 29 protons. Okay? So the little blue numbers in the upper right tell you how many protons are in each atom. Right? Now, the reason we do it this way is that I could be talking about a heavier nucleus, but I'm not going to, as we know, an atom with positive, with 10 protons in the nucleus has 10 electrons to then balance the charge and make it a neutral atom. We are only going to consider a case in which there is 1 electron that's going around a charge. Let me draw it a little bit. Let me need to draw this a little bit bigger and a little bit differently. So this is the charge ZE. And this is my classical orbit radius that Bohr was working on. And his idea was that he was going to consider circular orbits, circular electron orbits, right? And this electron is whizzing around the heavy nucleus, and it has a certain momentum P equal to mass times velocity. Turns out that electron velocities in atoms are non-relativistic, so we don't have to use relativity. Make it a little bit easier. By the way, this should be tangent to the circle, so I'll draw that a little bit more precisely. It goes off sort of like that. That's the momentum vector, and then there's the radius vector r, which we will label as r sub n. Right? So assuming that there will be different discrete energy levels that will correspond to different radii of orbits. And of course, as the radius of the orbit gets bigger, the total energy of the electron gets smaller because the kinetic plus potential energy is decreasing, as it is for planetary systems. Our energy of kinetic plus potential is much less than Pluto's total energy. So it works the same ways as in planetary motion. Okay, so he wanted to quantize the orbits, and in order to quantize the energies. And he assumed that because h has units of angular momentum, and electrons clearly have angular momentum. In fact, we can write down the classical expression for angular momentum is equal to r cross p, where r is we'll call it r sub n cross p, where p is the momentum vector. And if r and p are perpendicular, the cross product is just equal to the scalar product of the two quantities, and this becomes mv times r sub n, right? And that is an expression for the angular momentum of a particle going around in a circular orbit. Okay? Now, okay, so that's angular momentum. Now, Planck argued that h, which has units of, well, h has units of EV so we'll go right away. The units of h is 1240 EV over c nanometers. And momentum times distance has units of angular momentum because this is momentum times distance. And therefore, he said that would be, he assumed that the circular orbits have quantized, circular orbits have quantized values of angular momentum of L, of angular momentum, and they're going to be quantized in units of n times h divided by 2 pi, where n is equal to 1, 2, 3, all the way up. Right? N can be any value you want. Remember, n equals 1 to infinity, but the angular momentum is now quantized for the orbits. And they're quantized in units of h. H has units of angular momentum, so it makes sense that a multiple of h, or a multiple of h bar, would be a normal natural unit to quantize the angular momentum in the orbit. Yes?
Isn't the cross product of two vectors vectors?
Yes, it is. So, good point. Yes. So this should be. So let me. What he is quantizing is not the vectorial, but the magnitude. So we want to give the magnitude, and the magnitude or the size of that vector is quantized. Yes. Good point. Good point. All right. Okay. So that is Bohr's quantum hypothesis. Just like Bohr had his quantum hypothesis, right? Bohr's quantum hypothesis was that the energy levels of an oscillator are quantized in units of h times its frequency. That the energy levels of the oscillator were quantized in multiples of h times its frequency. He used the same similar idea, but saying that the angular momentum is quantized. And quantization is important because there's only 4 wavelengths that come out of here. And you've got to be able to predict those wavelengths based on a model if you want to understand what's going on. And so his model looks like this. Okay, so now we need to use the F equals ma equation, force equals Newton's second law, and write out exactly what the force is. Well, the electrostatic force of attraction between two charged particles is going to be equal to the product 1 over 4 pi epsilon naught times the charge of the nucleus, ZE, times the charge of the electron, which is E, divided by the radius separating the two particles. We call it Rn squared. Okay? And this, according to Newton's second law, is equal to mass times acceleration, but acceleration in a circular orbit is v squared over r. Okay? V squared over r is the acceleration for circular motion. Everybody remember that from mechanics? V squared over r? Yes? No? Yes? V squared. If you didn't, go back and check it. Even though a particle is not changing its speed by virtue of going around in a circle, it is accelerating because its vector direction is changing. So the vector velocity changes with time, therefore there is acceleration. Right? The magnitude of this doesn't change, but the direction changes. And a simple derivation shows that this is what we have. Okay. All right. Now, so we want to be able now to get to things that are related. I want to actually be able to calculate, what is the goal? So the goal is I want to calculate R sub n, and I also want to calculate the energies E sub n, right? Those are two things that I certainly want to try to get out of this theory, is how to calculate what is the radius of these quantized orbits. And also, as a result, what is the energy level of those orbits? Right? So once I know those, I then know that if I can correctly come up and get a value that's close, that agrees with this formula, where the coefficient out here is RHC, and I know what R, and I know what H, and I know what C is, I can see if my formula is correct. I'm going to have to predict this value based on this atomic model. That's sort of the direction we're going. Yeah.
Question about that. For your E sub n equals negative RHC, would that actually, wouldn't it be R sub H over 2 over 2, because E photon equals E sub n minus E sub 2? Like, then you apply it, and that's how you got E sub n equals negative RHC over N2.
Didn't quite follow you there.
Why is the RHC negative?
Oh, why is RHC negative? Yes, okay. The reason why it is negative is, because remember last time I said you have a choice of where, when you have a potential energy function, you have a choice of the constant. In other words, what is the potential at infinite distance from the force? And in our way of doing this, the potential U, and this is actually done in your E and M as well, the U at R equals to infinity should go to 0. Right? That if you have two charges, there's a potential energy of one with respect to the other. As those charges separate from each other with infinite separation, that potential goes to 0. So that's kind of like a boundary condition. That wasn't true in our finite square well potential, because we had the offset. We actually had a positive potential outside the box, right? What we're doing here is adding a constant so that the potential goes to 0. So for an electrostatic potential, then, if I draw up electrostatic potential, the potential energy curve looks like this. This is U of R is equal to minus 1 over 4 pi epsilon naught times 1 over R. And this is R, and this is U. And the reason we do it this way, number one, by taking the negative derivative, I get Coulomb's law, right? So that checks out. The other thing is I want the potential to go to 0 at infinity, right? And I also want the condition that bound states, which are electrons that are not free to leave the orbit, are trapped. And one way I'd characterize that is to say that total energy is negative. So in other words, for bound states, I have that the kinetic energy plus the potential energy, which we'll call U, right, U of R, is less than 0 for bound orbits. So it's just a way of characterizing the potential. I don't know an easier way to describe it than that. Now, having said that, this becomes these values E sub n, which are less than 0. So the quantized energy levels for the total energy, E1, E2, and E3 are going to be like this. Right? They are trapped between radius r equals 0 and r1, radius r equals 0 and r2, radius r equals 0 and r3. These are energies E1, this is energy E2, this is energy E3. Okay? And what we're trying to do now is to calculate these energy levels based on fundamental physics. You know, mass equals, force equals, Coulomb's law, force equals mass times acceleration, and see if we can actually derive this expression for this expression for the energy. But that's why we choose energy negative, because we want them to be correspond to bound states. And the potential is 0 at infinity, and the kinetic plus potential is less than 0 for bound orbits. They have negative energy. If I have something like this electron that's flying right across the vicinity of the electron, it has positive energy. It has energy up here. And that is a positive energy electron. It is not bound. It's going to keep going. So that's how we distinguish between bound and unbound. The bound states have negative total energy. The free states have positive energy. It's a way of distinguishing the two cases. Right? One case electrons are bound, the other one they're not. Okay, so we're almost there. We're almost there. So this is force. This is Coulomb's law applied with Newton's second law. And now I want to be able to solve for the radius. So what I'm going to do is I'm going to solve this equation for V. So over here, I can get that V is equal to N times H divided by 2 pi times the mass times the radius, r sub n. Okay? So the velocity is also quantized, right? If the radius is quantized, that means the velocity is also quantized. Probably indicates the energy is quantized, which it is. Huh? All right. Everybody clear with that? Solve that for V. Now I'm going to put V in down here. So this is equation 1. Actually, I need to write this a little differently. I'm sorry. This is equation 1. This is equation 2. This is equation 3. Okay. So now I put equation 2 into 3, which means that I am going to put in the velocity for this expression right here. And I can now then solve this for the radius, and the radius is equal to n squared divided by z times h squared epsilon naught divided by pi times the mass of the electron times the charge of the electron squared. So what have I done? I put this value of V, right, in here and solve this equation for Rn. Okay. Take this value of V, put it in here where I have a V squared, right? And I solve this equation for Rn. That's all I did. So this gives me the quantized, this by the way is a Z, not a 2. We'll put this like a Z. So my little bar indicates it's a Z. And so it's a nucleus with charge Z, but there's only one electron going around it. And so you can do this, by the way. You can take carbon atoms and you can ionize them, singly ionized, doubly ionized, triply ionized. You can knock as many electrons off of an atom as you want and be able to verify that, in fact, you've done so. You can isolate atoms with arbitrary number of electrons. Amazing what you can do. It's possible. So this is, of course, a single electron atom, right? Regardless of the size of the nucleus. All right, so this is our equation for R sub n. Okay, so now what we do is we want to calculate the energy, the energy and show that the energy is quantized. Well, it's probably not surprising that if the radius is quantized and the velocity is quantized, then the total energy is quantized. Because kinetic energy is mv squared, 1/2 mv squared. Potential energy goes like 1 over r. R is quantized. So the energies are going to be quantized. Right? Now we just have to show that they're the right energies to calculate these wavelengths that we're measuring. So that's the path going forward. Okay, so let's write down the total energy. So I'm going to write down that the energy of the electron in the nth excited state is equal to 1/2 mv squared minus 1 over 4 pi epsilon naught times z over e squared divided by r sub n. Everybody? This is kinetic plus potential. This is equal to kinetic energy plus potential energy. Okay? And since I'm going to assume that, not so, I will show you that since U is equal to minus 2 times the kinetic energy, we'll assume this is true right now. And this, of course, is the potential, and this is the kinetic. Then I can write this as that En is equal to minus U over 2 plus U, and notice I dropped the R right now, which is equal to U over 2, which is equal to minus Z times E squared divided by 2 times 4 pi epsilon naught times R sub n. Right? Or eliminating R sub n from this equation right here, which I'll call equation 4, then I can use equation, let's say use equation 4 to eliminate R sub n. And I get that this is equal to minus Z squared e to the 4th times the mass of the electron divided by 8 epsilon naught squared h squared times 1 over n squared. Okay? And that's my expression for energy. Okay? Okay? Okay. So, why is potential energy equal to minus twice the kinetic energy? Notice that, let's see. Notice in this equation right here, I can say that mv squared is equal to, I've multiplied through this by r, right? Is equal to 1 over 4 pi epsilon naught times z e squared divided by r. And this is equal to, this is the potential energy, U of r, well, with a minus sign in here, because the force is radially inward, there's a minus sign in here. So what I then get is that this says that the potential energy, U, is equal to, this quantity right here is twice the kinetic energy, 2 times the kinetic energy. So the potential energy is equal to, sorry, let's go back here a second. Let's go back here a second. U of r is equal to minus 1, is equal to minus z over e squared divided by 4 pi epsilon naught times r, or we could say r sub n, right? That's the potential. So this right here is minus u for the force. This expression is 2 times the kinetic energy. These two things are equal. So u of r is in fact minus twice the kinetic energy. Okay, so I use this fact only to show you that this is true for circular orbits. It's true that the potential energy is minus twice the kinetic energy. Okay, and that leads to this. That leads to this. To this expression. Okay, so now what we want to do, what we can do is return to the Rydberg formula, And remember that Rydberg had observed that this number R was 1.09 times 10 to the 7 inverse meters. And this is what, in fact, we have to show from the Rydberg formula, where 1 over lambda is equal to R times 1 over 2 squared minus 1 over n squared. Right? For these 4 wavelengths, lambda sub n. Right? And so now we have a way to do that, right? Because using the Bohr theory, we know that hc over lambda, or lambda n, if you want to call it lambda sub n, is given by the difference in the energies, we will say from En minus E2, which is was what the formula is telling us. And so now what I can do is we can write this as this is equal to z squared times e to the 4th times n sub e divided by 8 epsilon naught squared times h squared times 1 over 2 squared minus 1 over n squared. Right? Right? Okay, now what I do is if I divide this quantity, this whole thing, this is equal to R times HC. So I can equate these two coefficients, and I can evaluate what R is going to be. R is going to be equal to H cubed. It's going to be equal to Z squared times e to the 4th times the mass of the electron divided by 8 epsilon naught squared times c times h cubed. Right? So I simply divide this by hc, and I get my constant R. Now, what I can do is, and we'll look particularly at hydrogen, so we'll set z equal to 1, right? And these are other constants or fundamental constants that I know. And if I evaluate them, what I get is 1.09 times 10 to the 7 inverse meters. Right? This was the value that Rydberg found experimentally. Right? But Bohr is now able to explain it. He's able to tell you why this formula of Rydberg's is correct, wherever I wrote it down, the first place I wrote it down. He's able to say why this formula of Rydberg's is correct. It's because the electrons are being excited to a higher energy level in the force of a Coulomb potential. There's a Coulomb force field holding the electron in its orbit. The total energy of the electron is changing when the electron gets knocked into a higher orbit by the electron in the discharge tube, and as a result, that electron will decay back into lower energy levels. Right? So, QED, he proved it. Right? He basically said the reason why this formula works is because this is the picture of what's going on. I have quantized the energy levels by quantizing the angular momentum, and it gives me the correct wavelengths that Rydberg found. And I can derive those values from the fundamental constants, which is M, E, C, H, and E, and epsilon. Okay? So that's a theory. That's a successful theory, right? And he deserved a lot of credit for that. There were problems with the theory. There was one problem in particular, and that was a couple problems, and that one is that it didn't really explain the multi-electron atom. So what happens when there are two electrons? What is the energy? How do you calculate? We still need to calculate E sub n with two electrons. With two electrons, right? Even helium is the simplest one, right? Helium has 2 electrons and 2 protons, right? So you might think that there are 2 electrons, they're both in the ground state, and therefore they both see a charge of Z equals 2, right? And I calculate the energy levels, and they give me the wrong wavelengths. Fails. The theory fails. It fails when you go to the multi-electron atom. It also fails when, on conceptual grounds, that where did this come from? Right? Why are the orbits circular? Why can't they be elliptical? You know, planets have elliptical orbits. Comets have elliptical orbits. Why can't the electrons? It's the same type of force field. It's 1 over r squared. It's the same for gravity as it is for electrostatics. So this is sort of like, well, I don't know. That's not really a good theoretical foundation to say that all orbits are circular. But more importantly, it fails. It fails when you try to apply it to helium, lithium, atoms with more than 1 electron. The theory just breaks down. So it was clearly a step in the right direction. People began to realize that orbits did have to be quantized, but the failure of the model was quite apparent. So something had to be done about that, and of course along came Erwin Schrödinger, and Schrödinger decided to tackle this problem by solving his own equation. Remember the differential equation. Right? So Schrödinger came up with the idea that what we really need to do is to solve the wave equation. Right? And the wave equation can be summarized by saying that, if I were to write this out, that the way we did it before is that minus h bar squared divided by 2m times the second derivative of the wave function with respect to x. And then we said there was a potential energy, I'm going to put a space here, I'll show you why in a minute, plus there's a potential energy u of x times psi is equal to energy times psi. Right? And he wanted to find out is, can we get quantized energies in a Coulomb force field, right? Coulomb force field. Right? And of course, what we mean by that is that the force is equal to 1 over 4 pi epsilon naught times 1 over r squared. Right? That's a Coulomb force. And so he wanted to use the Coulomb force, which in radial terms this would be plus the Coulomb potential is minus 1 over 4 pi epsilon naught times r, where r is the separation between the charge of the nucleus and the electron. So the electron can still be thought of going around in orbits if you want to think of it that way, but the potential energy term is right here, right? Now, still have 2 minutes left, so I'll stop in just a second. So, in addition to this now, we have to solve the problem in 3 dimensions. Right? This is a 1-dimensional equation that we've been doing up till now. But in 3 dimensions, remember this was equal to px squared times psi, and in general, momentum in 3 dimensions squared is the Pythagorean theorem sum of px squared plus py squared plus pz squared, right? So I have 3 terms like this. I have minus h bar squared over 2m times the second derivative of psi of x, y, and z. So now it's going to be a function of 3 variables with respect to x, and these become partial derivatives, plus the second derivative of psi with respect to y squared, plus the second derivative of psi with respect to z, which we write this way, minus 1 divided by, now I add in the potential energy term, negative 1 over 4 pi epsilon naught times r times psi of x, y, and z is equal to E times psi of x, y, and z. Okay? And this is the Schrodinger equation for I need another parenthesis here, the Schrodinger equation for a particle in a Coulomb potential. Right? And we're going to not solve it, but we're going to show you what the solutions look like. It turns out that the energy levels that were derived by Bohr are exactly the same for hydrogen. And that's a good sign because Bohr was able to get the correct wavelengths from transitions. So the energy levels are in fact correct, and they are going to be the same as what Bohr found. But the other character features of the particle motion are in fact different, and therefore this is the solutions to this equation is what is now used to describe the orbits. And out of this comes the quantum numbers that are associated with electron in the atom. You know about orbitals, for example. You know about suborbitals or different ways of describing the energy levels in chemical bonds. All come from the solution to this differential equation that was derived by Schrodinger. And once he was able to show that he got the correct energy levels from this equation, then he got the Nobel Prize, number one. But number two, he became used for molecular physics, for solid state physics, for the theory of conductors, the theory of semiconductors, the theory of chemical bonds. Everything came out of this equation on an atomic level to explain all the properties that we know about physical matter. And that's worth a Nobel Prize. Okay, we're at 3:16. Homework due tonight, test on Thursday. Make sure you arrive on time.